This is my 547 which I've restored a couple of years ago, and I got back into it to uncap it. What I mean by uncap is this: removing all the modern electrolytics in it and reforming the original caps. I have removed every capacitor which I have put in place as a replacement and reformed the original ones. And I was going through the basic test procedure and checklist for the instrument, and I figured out there's something interesting. I don't have any of the delayed trigger functions. The delayed trigger functionality is dead. That's the A trigger, Alt, B, and then B intensified by A is dead. So do the Alt, and so do the delay trigger. So let's look into it. So I thought, that would be a good video to show you how exactly to troubleshoot a delayed trigger, especially in 547. So the first point to start is to put this guy into delayed trigger and then come back and see if I'm seeing any delayed trigger pulses coming out of the front panel. If that's not there, my delayed trigger circuitry itself is bad. But if I have a delayed trigger here, then it's something to do with the sweep switching multivibrator or something else beyond that. So let's see if I have some signal out here. Probing my delayed trigger, absolutely no signal. To confirm my A sweep is working, I'm going to test the signal over here on the A sweep output, and I do have signal. So my sweep is working. It's time to troubleshoot the delay trigger circuitry. Okay, let's look at the basics of how this whole delay trigger is done. Let me draw a basic oscilloscope, with this being the CRT, unfortunately in a potato shape, and we will look into the horizontal deflection plates. We assume that the vertical deflection plate is already supplied with the right signal for displaying the waveform. Now this is connected to my time base, and I have a signal which is coming in here like this to display my waveform. This is the basic oscilloscope. In delay trigger, what you get is an option to zoom in any portion of the waveform across the trace, and which basically means you can pick any point of this waveform and then expand it and inspect it in detail at a different sweep rate, which basically means you can select any point in the whole sweep and then zoom into the waveform. Now this is done by using an additional time base. In most Tektronix 500 series scopes, the main time base is called as time base B and the auxiliary time base is called as time base A. Now the way it's done is you have a port in the front panel which controls your delayed trigger or the delay trigger multiplier, which basically says where in the sweep you're going to start triggering the A time base, or where in the horizontal section of the waveform you're going to start triggering your second time base. And the second time base is generally configured to be at a much faster rate so that it gives you a zoomed in waveform. Or say for example, if I adjust the delay multiplier to trigger at this phase, which basically means here, as soon as the ramp from time base B reaches this place, that's when it's going to trigger time base A, and then that's going to give you a much faster sweep, resulting in a waveform which is going to be something like this, a much more zoomed in waveform. So that's the fundamental idea behind delayed trigger. There are mainly three components if you look into it. Of course, the main time base, which is time base B, and the auxiliary time base, which is time base A, and then the point at which the auxiliary time base is controlled by the delay multiplier knob in the front panel. Now, how this is implemented in an oscilloscope or in a 500 series oscilloscope slightly varies from model to model. In most of the models, when you adjust the time for the trigger or the delay for the trigger, you put the scope into a mode called as B intensified by A, wherein the scope will intensify or the trace will be brighter on the portion which is going to be zoomed in. So as you adjust the delay multiplier knob, the intensified portion can slide across the screen, which means it's going to slide across here. And then you switch to a delayed trigger wherein it'll hand over the horizontal control to time base A, which is a much faster time base. I'm going to show you a zoomed in waveform from the original one, or from the point where you decided to do the trigger. So that's the fundamental idea behind it. In 547, it's a little bit more tricky. where they have an option to do something called as an alternate mode. This is very similar to what you do in a dual trace plugin, where you take vertical channel 1 for one trace and vertical channel 2 for the second trace. 547 can actually display the main waveform in the first trace and the zoomed in waveform on the second trace. Now this is made possible by a sweep switching circuitry, which is special to 547. That's the fundamental principle behind delayed time base and specifically 547 alt delayed sweep. Let's get into the schematic and see how it's done. Okay, this is the delayed pickup circuitry in 547. This is where you're getting your main sweep or output from B sweep or B time base, so called, which is connected to this tube here. And this is a whole comparator section. The other side of it is biased statically using your delay multiplier pot. That's what you see here. And then both of them have a long tail configuration sitting through this current source, which is this tube. Now, long story short, what happens is as you adjust the delay multiplier pot, the point at which this tube turns on will vary along this ramp, and at a point where it's going to start getting turned on, it'll start conducting through this path, which means it's going to draw current through the tunnel diode plus the inductor and the resistor here, which means the tunnel is going to carry a current which will trigger the tunnel diode once the current through it passes through the peak. And once that happens, it's going to drop the current through it down to the valley. That's going to be a sharp downfall because of the tunnel effect, and that sharp downfall will be amplified by or picked up by this coil, and it's going to send it back to this transistor, which is going to see a spike in its base, which will get amplified and available in the emitter. I've taken a waveform even from the collector of this transistor to show you what exactly is the output waveform here, but it's a rather sharp pulse like you see here, which is then amplified and passed out as delayed trigger for the front panel. And then that's what goes into the rest of the delayed trigger or horizontal switching circuitry as a delayed trigger. Now, as you adjust this control, the point at which this whole action happens will vary along the sweep ramp. So this is the circuitry for 547, sweep switching multivibrator trace separation amplifier. Now, this is again, I would say very specific to 547 because it does offer you an alt mode to display both the traces on the screen. When I say both the traces, what I meant is the normal as well as the delayed sweep, which is the magnified sweep. Let's see how it works. Your B sweep sawtooth comes in here, and your A sweep sawtooth comes in here. And the output to the horizontal amplifier is taken from this portion. And which sweep is used to fire your horizontal amplifier is controlled by this multivibrator. By default, when you put into a delay trigger mode, what happens is your delay pickoff circuit triggers your time base A, and that will deliver the sweep here. And then rest of the circuitry around this is used to control the timing and make sure that it displays one sweep after another, and the sweeps are synchronized between both the time bases. And there is an interesting portion of schematic right over here, which basically separates the traces when you're in alt mode, which means when you put into alt mode where you're seeing the delayed sweep as well as the normal one, you can adjust the separation between both of them vertically on the screen, and that is achieved by this particular section. Now, I'm not going to get into the very specific of what resistor and transistor or a tube does what, because it's already explained in the schematic, but if somebody wants to understand the details, let me know. So that's about it. Now let's get into troubleshooting this. Okay, let's get into the portion where the delay trigger is located, and that's exactly over here. We have the tubes, which is used for delay trigger here, plus the transistors, and the most key component is this little guy, the tunnel diode, the 2.2 milliampere tunnel diode, which is used for generating the delay trigger pulse. So let's probe through these points and see if you're getting the right signals across and figure out why is it broken. So to test it, I could straight away check the signal which is coming here at this part of the tunnel diode. The top side of it is the B plus, and the bottom side is where I'm expecting a square wave based on the position of the delayed multiplier pot. So let me check the signal here. That's where my oscilloscope is plugged into. So I do have the pulse, and as I adjust the delay multiplier, the shape of this pulse will change, which is happening. So that means my comparator and my basic delay pickoff circuit is working. So let's see what is the output of the next stage, which I should see a pulse if the tunnel is good. Now I have moved my probe point to Q424. That's where the pulse should come out because of the tunnel diode. And if you can see, there's a small little tiny inductor sitting deep inside. That's the one in conjunction with the tunnel diode creates that pulse. And unfortunately, what I see in the scope is still a plain simple square wave, which points the fault directly to the tunnel diode. Now, why the square wave will not cause a trigger or a delayed trigger is because there is a differentiator down the line in the circuit which passes only the high frequency pulses. The reason for doing that is to make sure that you are triggering precisely at the right time, and you're triggering with a very sharp pulse which comes only from the tunnel diode. So let's pull the tunnel diode and test it out. This is a tunnel diode of my 547. I'm going to show you how a good tunnel diode looks versus a bad one. Now there is a very simple way to test this. You don't need a curve tracer or oscilloscope. Alan did a beautiful video on how exactly to troubleshoot or test a tunnel diode. I'm going to link that video in the description. But here I'm going to show you how exactly a good versus a bad tunnel diode looks. Let's try the bad tunnel diode. I'm going to increase the current through this. This is my ammeter sitting in 10 milliampere range. Let me start increasing the current through this. You can see that's all I had as a dip. It was not much there, but it did have a dip in the current, but not strong enough. Let me show that here again. That's it. So I don't know if it should be called as a weak tunnel or maybe a bad tunnel diode, because the valley itself is not steep enough. Let's see how a good 2.2 milliampere tunnel diode behaves. You can see the current starts picking up right away, and you can see the valley, and it's repeatable. There you go. Let me do it once again. And this is what is needed in the scope trigger to have a constant or continuous delay trigger. Whereas if I put the bad diode back again, you can see the difference. First of all, it needs quite a lot of potential across it to start the current. 2.2, that's it. That's an easy way to figure out if a diode is bad or good. The earlier serial number 547s had 1D2 in them, which is what I have in my hand. And the replacement which was used in the later serial number is this particular model, Tech Part 152040200. Now, one thing you need to be a bit careful about it, the polarity of these diodes. The 1D2, this is the anode, the left side, and the right side is the cathode. Whereas on this part, it's exactly the other way, which is what you would typically expect. So you need to remember the polarity. Okay, that's a new tunnel diode in there, and that fixed the issue. Now, just to show you what happens when you have a proper tunnel, where you see the peak or the spike, or what you call as the whole tunnel diode effect. Let me show you the waveform right of the tunnel diode. By the way, if you look at it, the tunnel diode was actually installed on top of another lead because I didn't want to put too much heat onto the tunnel by soldering it into the ceramic strip, so I just put it slightly off it. It's gonna add a little bit of inductance onto the whole lead. This is the waveform of the tunnel diode, and you can see this spike. That's happening because of the tunnel effect or the tunnel diode and the inductor. So this is what gets coupled all the way as a delayed trigger pulse. It's the same mechanism which happens even in the trigger and the sweep section. And if you like to see what exactly is the pulse which gets passed on to the trigger section, or to trigger the delayed sweep, is this particular one. This is the differentiated signal out of the tunnel diode. Now, if you're wondering why did I do all this circus for, let me show you what is the outcome. So standard oscilloscope display. Time base A is selected in the horizontal display selection switch, and this is the time per centimeter for time base A. And time base B controller is right down here, which I'm not going to be able to cover in this shot. Now let's start with the basics. Time base A is what I'm using now, and I can of course adjust the trace to see whatever I want to see. So let's say I'm going to zoom in into this level. Now I can go to time base B and then set whatever level of the waveform I want to see it as. Okay, now I can zoom in the same waveform by altering the sweep between both the time bases like this. So what you see on the top is time base A, and what you see on the bottom is time base B. And then there's a trace separation control using which I can adjust the gap between both the waveforms. Now there is no delayed trigger here. This is still standard triggering on both the time bases, but this is doing alternate between both the time bases. Now let's go to the next step, which is B intensified by A, which means my main time base is going to be A, or rather I'm going to use A time base to zoom into the waveform. Okay, so if I switch in here, you can see the waveform gets highlighted, and then as I move the delay time multiplier here, you can see I can specifically narrow down into a portion of the waveform. Right, that is B intensified by A. And then you can come straight down here and go to A delayed, which means I'm actually seeing the portion which is zoomed by the delayed trigger. Or you can see both by switching between the alternate, wherein I can switch between B intensified by A and the delay trigger and have a live view of my waveform. So as I move the delay multiplier, I can zoom through the waveform. So this is exactly what I was after. Another example of the alt trace with delay and a little bit more of zoom in. Now the flickering is due to the frame rate between the camera and the scope, and you can see I can actually zoom in to the specific portion of this pulse, and if I adjust the intensity, you can actually see the portion which I'm really trying to zoom in. And as I move forward, shows me the waveform where I am actually trying to zoom in. So hope that's useful, and thanks for watching, and take care.